Hi, and welcome back to this new lecture in our series on mathematics. In the last class, we discussed linear inequations. Let's start with a quick recap of what linear inequations are before we start practice questions. Now, an inequation is a representation, is a mathematical representation that two quantities are not equal. An equation would be a representation that two quantities are equal, and an inequation that the quantities are not equal. A linear inequation has linear expressions in the inequality. What does that mean? If you look at these two examples, the degree of these variables, there is a variable x and then there is variable y, these two are both having a highest degree of 1, and that would make it a linear inequation. So x plus y is greater than 7. The second example also is linear because the highest power of the variable y is 1. So 3y minus 8 is less than minus 11. So that makes it a linear inequation. We discussed four important rules that can be used to solve linear inequations algebraically. And what are they? Let's do a quick summary. Adding the same number to both sides of an inequation does not change the sign of inequality. What does that mean? Really quickly, if I have an inequation y is less than or equal to 7, adding the same positive number, let's say I add square root of 3, which is a positive number, to both sides, the inequation does not change. So y plus root 3 is less than or equal to 7 plus root 3. I added root 3 to both sides. Similarly, subtracting it from both sides does not change the inequation. So I have subtracted square root of 3 from both sides. Now multiplying or dividing both sides of the inequation by the same positive number does not change the sign of inequality. What does that mean? If x is greater than or equal to minus 3, I can multiply both sides by positive 4, and this is what we get. I have multiplied both sides by plus 4, and the same applies for division as well. If both sides of the inequation are divided by the same positive number. The last condition is multiplying or dividing both sides of an inequation by the same negative number reverses the sign of inequality. What does that mean? Let's take another example. Y is greater than root 5. If I multiply both sides by, let's say, negative 2, then the sign reverses. I have multiplied both sides by negative 2, and what was greater than here has become reversed and has become less than. And that is the effect of multiplying both sides or dividing both sides of the inequation by the same negative number. So these are the four conditions which we use to find solutions to linear inequations. Now let's jump into practice questions. Here is the first set. So we have to look at the operation performed here and fill the blanks with the proper sign. So what signs do we have? So we can use this or this or this or this. Now look at the first one. P is greater than Q. P and Q are real numbers. P is greater than Q. And what has happened here? We have subtracted negative 11 from both sides of the inequation. So the inequation should not change sign. So it should remain greater than. Because we have subtracted, so the inequation does not change sign when the same number is subtracted from both sides. Second one, a is less than or equal to b. Now what happens here? We have added square root of 3 here and we have added square root of 3 here. So we have added square root of 3 to both sides. And the inequation does not change sign. It remains less than or equal to. Now let's look at this. X is greater than y. That is the given uh, inequation. And we have minus 9x here and minus 9y here. Now I recommend every time you see a practice question that you pause the video and try to do these questions. And you can always look at my solution if you get stuck, but do try these questions by yourself. What has happened here is we have multiplied both sides by a negative number, and that's why we get minus 9x and minus 9y, in which case what was greater than here becomes less than, because we multiplied both sides of the inequation by a negative number. Now here a is less than b, that is given. Now both sides are divided by the same positive number, which means the inequation does not change sign, it remains less than. So this is the way in which you can look at the operation being performed and decide whether the inequation changes sign or not. Next set of questions involves deciding what kind of values of the number k will make the following statements true. If a is greater than c, that is given, if a plus k has to be greater than c plus k, what values of k can you have, or what values can k take? Now adding any number, positive or negative, to the two sides of the inequation will not change the inequality, will not change the sign. So k can be any number, k, any real number. It can be positive, negative, rational, irrational. K can be any real number and this will still be true. I can write it as just the second question. A is less than or equal to b, that is given. A minus k, excuse me, is less than or equal to b minus k. For what values of k will that be true? Again, we are subtracting the same number k from both sides. So k can be any real number. It can be positive, negative, integer, rational, irrational, anything. It will still be true. Third question, x is greater than y, but xk is less than yk. So multiplying both sides of the inequation by k cause the inequation to change sign. Earlier it was greater than, then it became less than. And it's only possible if k can have negative values. So k is a real number and k is less than 0. And only then will this be true. Let's look at the fourth question. If a is less than b, and if a divided by k has to be less than b divided by k, it's possible if k, it's possible if both sides of the inequation are divided by the same positive number. So what kind of values can k have? It can have positive real values. So I can write it as k belongs to the set of real numbers and k is positive. The last one is a bit different. You see, we start with an inequation, x is greater than y, and then we end up with an equation. X is greater than y, but then x multiplied by k becomes equal to y multiplied by k. How does an inequation become an equation. So think of two numbers. Let's say 5 is greater than 3. Under what circumstance will be 5 times k become equal to 3 times k? Think about that. And if you have not paused the video by now, do pause it and think about what values of k will make an inequation become an equation. And the answer is this: it's possible only if k is 0. So if k is 0, both sides of the inequation become um, equal to 0, so it becomes an equation. So these are the uh, this is the way you can find the value of k in such questions. And again, we are using the same four rules of inequations to answer such questions. Our next question is this. So we have essentially two separate conditions we need to consider. The first inequation is this: negative 5 is less than or equal to 2x minus 3. And the second one we have to consider separately is this: 2x minus 3 is less than or equal to x plus 2. And then we see which values of x will satisfy both conditions. So let's start with the first. Negative 5 is less than or equal to 2x minus 3. By adding 3 to both sides, you end up with this. By dividing both sides by positive 2, you end up with minus 1 less than or equal to x. That is what we have. How did we go from here to here? We went from here to here by adding 3 to both sides. How did we go from here to here? Well, it was just simplification. We added negative 5 and 3 and made it negative 2. How did we go from here? Dividing both sides by 2. So this can also be rewritten as x is greater than or equal to negative 1. So this is the first result when we compared these two. Now let's take a look at what this inequation gives us. This one, and that we have 2x minus 3 is less than or equal to x plus 2. So 2x minus x is less than or equal to 3 plus 2. X is less than or equal to 5. This is the second condition. So what we have is, by looking at the conditions given, we realize that two conditions have to be satisfied to find a common solution. One is, this says x has to be greater than or equal to negative 5, and the second condition says that x has to be less than or equal to positive 5. So combining these two, we will get the solution set consists of values where x, I'm sorry, is not a real number. It should be z, because it's given that x belongs to the set of integers. So z represents the set of integers such that minus 1 is less than or equal to x, and that is less than or equal to 5. So it can also be written as minus 1, 0, 1, 2. These are all the integers which satisfy the condition negative 1 less than or equal to 5 less than or negative 1 less than or equal to x less than or equal to 5. So we can write it in the rule or set builder form, or we can actually write out the elements in the solution set. Next question is this. Now notice, you should always keep in mind before you start doing these that x belongs to the set of whole numbers here in this case, and this is the replacement set, and whatever solution set you find must be part of the replacement set. This is, whatever solution you find must be whole numbers. So keep that in mind before you start solving these things. So minus 1, let's take the first condition. Negative 1 is less than or equal to 3 plus 4x. You subtract 3 from both sides, you get negative 4 less than or equal to 4x. You divide both sides by positive 4, you get this, or x greater than or equal to negative 1. That's the first condition. The second condition is 3 plus 4x is less than 23, which means if you subtract 3 from both sides, you get 4x is less than 20 and x is less than 5. So the replacement set is the set of all whole numbers, and therefore the solution set is this, such that minus 1 is less than or equal to x, which is less than 5. Remember, when you write it like this, you are indicating that negative 1 is part of the solution set, but 5 is not part of the solution set because x cannot be equal to 5, it is less than 5. By looking at it, you can actually list the elements in the solution set, and what will they be? Negative 1. You can't include negative 1 because remember, we have to make sure that these are whole numbers. Whole numbers start with 0 and we can go up to 4. 5 cannot be included because it should be less than 5. Negative 1 cannot be included because whole numbers start from 0. So these become the elements in the solution set. Let's go to the next question. So you must make it a habit to notice what the replacement set is. So let's recognize that and write it. The replacement set which indicates the set of whole numbers. And what are whole numbers? 0, 1, 2, 3, etc. It's an infinite set starting from 0 and consisting of integers. So given the replacement set, what is the largest value of x which satisfies the given inequation? So let's see. 2 multiplied by x minus 1. So let's open these brackets and write it as 2x minus 2 is less than or equal to 9 minus x. So adding x to both sides. So how did we go from here to here? adding x to both sides. Remember, x can be positive or negative, but the inequation, the sign of the inequation does not change when you add the same number to both sides. So we get 3x minus 2 is less than or equal to 9. And then we from there we can go to 3x is less than or equal to 11. And how do we get that? That is obtained by adding 2 to both sides. Again, the inequation does not change sign. So we come to that. So x has to be dividing both sides by 3, you get this. But remember, x has to be a whole number. It can't be a fractional number. So the highest value of x, now when you actually perform this division 11 by 3, you will notice that 11 by 3 is between 3 and 4 because it's 3 point something. It's between 3 and 4. So the highest value of the highest whole number satisfying the inequation x is less than or equal to 11 by 3 is x. So think about what is the highest number. If you put x is equal to 4, then it will not be satisfied. So it has to be 3. Let's go to the next question. Solve the inequation 12 plus 1, 5 by 6x is less than or equal to 5 plus 3x. X, it can be any real number. So once again, we will recognize what the replacement set is. It's important to know this. Otherwise, we may represent the wrong answer. So the replacement set is x belongs to R, which is all real numbers. Then we will proceed to find the solution set. How do we do that? We're starting with 12 plus. I'm going to write 1 and 5 by 6 of x as an improper fraction. It becomes 11 by 6 x is less than or equal to 5 plus 3x. I subtract 5 from both sides and then bring this term to the right hand side. I'll end up with 12 minus 5 is less than or equal to 3x minus 11 by 6x. Using the LCM, we can simplify this. It's 18x minus 11x by 6. So multiplying both sides by 6, we get 42 is less than or equal to 7x. Now you divide both sides by 7, you get 6 less than or equal to x. Another way to write it is x is greater than or equal to 6. So since it's set of real numbers, we can say any real number equal to or greater than 6 becomes part of the solution set. So let me write the solution set here. X belongs to a real number such that x is greater than or equal to 6. Next question. Solve and graph the solution set of these conditions. So let's consider the first two. Remember, the replacement set is x belongs to R. So let's recognize that and write it here. Replacement set is the set of all real numbers. First, let's consider 2x minus 3 less than x plus 2. You can subtract both sides of the inequation by x and you get 2x minus x minus 3 is less than x plus 2 minus x. That leads us to x minus 3 is less than 2. You can add 3 to both sides, giving us this inequation. X has to be less than 5, and that's the first one. Let's look at the second one, and that is x plus 2 must be less than or equal to 3x plus 5. And going through the same steps, you can add negative 5 to both sides and bring this x to the other side. You get negative 3 is less than or equal to 2x. Divide both sides by positive 2. You get negative 3 by 2 is less than or equal to x. Or this can be rewritten as x is greater than or equal to negative 3 by 2. This is our second condition. So whatever solution set we find must satisfy both of these conditions. What are these two conditions? This is the first one, x has to be less than 5, and this is the second condition, x has to be greater than or equal to negative 3 by 2. So how do we represent this on a graph, on a number line? So if you have this is 5, 4, 3, 2, 1. So we have this. So let me remove these dots because they may be misleading. So this is our number line. Remember, it has to be less than 5 or greater than or equal to negative 3 by 2. So negative 3 by 2 is negative 1.5. It starts here. This is negative 3 by 2. And 5 is over here, but it has to be less than 5. So I put a hollow dot. This is a solid dot. And at 5 we have a hollow dot, and between the two I draw a line. Now I'm trying to draw a line as straight as possible, but you can use a scale to draw a nice line, and that becomes the solution set on the number line representing these set of numbers. So 5 is not included, negative 3 by 2 is included in the solution. So this is the answer for this question. Solve and graph the solution set of the given inequations. There are two of them. This is the first and this is the second. So let's take a look at it. As before, we recognize the replacement set as x belongs to R, which is all real values of x. Take the first inequation, 2 and 2 by 3 less than or equal to x plus 1 by 3. Subtract 1 by 3 from both sides. You get negative 2 by 2 and 2 by 3. Negative 1 by 3 is less than or equal to x, because we have subtracted negative 1 by 3 from both sides. You get minus 8 by 3 minus 1 by 3 is less than or equal to x. This leads us to minus 3 is less than or equal to x, or x is greater than or equal to negative 3. This is the first condition. Let's take a look at the second, that is x plus 1 by 3 is less than 3 and 1 by 3. By subtracting 1 by 3 from both sides, I end up with x is less than 3. So you have two conditions. This is the first, x has to be greater than or equal to negative 3, and this is the second, x is less than positive 3. And remember, x can be any real number. So in set builder form, we can write the solution set as follows: consists of all values of x such that x is a real number and the values of x are between negative 3 and positive 3. Positive 3 is not included, negative 3 is included. So as before, I can start with a 0, 1, 2, and on this side we have plus 1, plus 2, plus 3. Plus 3 is not included, negative 3 is included, so I color it like this. It's a solid dot, and then a line between these 2 points will give us the representation on the number line. Next question. Solve and graph the solution set of the following two conditions. So there are two separate inequations. There is this and there is this. As before, we recognize the replacement set. The replacement set is given here. It is the set of all real numbers. Now let's take a look at this inequation first. So you have x plus 5 greater than or equal to 4 multiplied by x minus 1. I will open the brackets out on the right hand side and rewrite it as 4x minus 4. If I add 4 to both sides, what do I get? I get, remember, I'm adding 4 to both sides. X plus 9 is greater than or equal to 4x. So by subtracting x from both sides, I get 9. So that's x plus 9 minus x is greater than or equal to 4x minus x. And I'm illustrating it with such detail so that you recognize at every step which of the rules we are using to simplify this. So x plus 9 minus x is greater than or equal to 4x minus x. We have subtracted both sides of the inequation by x. So we end up with 9 is greater than or equal to 3x, or 3 is greater than or equal to x. And this can even be written as x is less than or equal to 3. This is what the first inequation gives us. Now let's see what the second inequation gives us. This is our first condition. What is the second condition saying? So it is 3 minus 2x is less than negative 7. By adding 2x to both sides, we end up with 3 minus 2x plus 2x is less than negative 7 plus 2x. I have added 2x to both sides, so I end up with 3 is less than or equal to negative or less than negative 7 plus 2x. The next step is to add 7 to both sides. of the inequation. So it becomes 3 plus 7 is less than, which gives us 10 is less than 2x, so 5 is less than, and this can even be rewritten as. Now I would like you to pause the video here and think about how we can find the intersection of these two solutions. Remember, the word and here tells us that whatever solution we finally find must satisfy both inequations. There are two inequations here. There is the first inequation here and the second inequation here. And the solution set we finally find must satisfy both inequations. Now you think about what we can come up with. X has to be less than 3, says the first condition, less than or equal to 3. The second condition says x is greater than 5. So if you try to represent it on a number line, and I'll draw a rough number line here to illustrate my point. Um, so the second condition says that x has to be greater than 5. It has to be somewhere on this side of the number line. And the first condition, x is less than or equal to 3, says that x has to be somewhere on this side of the number line. Now, can you find values of x which satisfy both conditions? You cannot. How can it be more than 5 as well as less than 3? So that is not possible. So this solution does not exist. So we can conclude that the solution set is an empty set. That means it has no solution. It's a null set or an empty set. No solution possible. Next question. If the diagram shows inequations A, the one inequation A on a real number line, write A in set builder notation. You look at this. Now there is some interesting things you have to observe in this representation. This part is easier to analyze. If you see a solid rectangle with straight sides, there is a straight side here and a straight side here. And what does that mean? It means that the values 2 and 5 are both included. So this part here represents values of x between 2 and 5 where 2 and 5 are both included. And how do I know 2 and 5 are included? Because it's got the straight edges here. What about this part of the number line? You can see that it goes from negative 2, negative 1 here to negative 4, but the edge on negative 4 is curved, indicating that negative 4 should not be included. So how do we write that? We can write this as follows. It's negative 4 is less than x less than or equal to negative 1. You see, at the negative 1 side, the value negative 1 is included. That's why this became less than or equal to. Whereas negative 4 is not included. So it is just less than. So these are the two sets of values that are included in set A. So how do we write this in a set builder notation? So we can say that A is a set of all real numbers because everything between these numbers are included, such that it has to be between -4 less than and or I should not be and, or it can be either in this part of the graph or it can be in this part of the graph, right? So that's how we are writing it. So or 2 less than or equal to x, and because we are talking about set notation, I can replace this with union of two sets. So this represents, and you must be familiar with this notation from your chapter on sets. So this represents the union of two set of values, one between -4 and -1 and one between 2 and 5. So what about this? A dash is the set of all values which are not in A. It should not be included in A. So how do we represent that? So A dash consists of all values which are real numbers, such that it can be all the values including -4, this side of the number line can be included in A dash. Then all numbers here between -1 and 2 can be included in A dash. And how do we represent that? Union -1 less than x less than 2. That is all the numbers over here. And finally, we have to include all the numbers which are on this side of the number line in A dash as well. So I put another union and say x is greater than 5. So there are three regions of the number line we can include in set A dash because they are not in set A. Please observe how the sign less than or less than or equal to is used carefully. And there is one mistake here. It should be x should be less than or equal to -4, and that makes it this part of the number line. This part of the number line consists of all values of x which are less than or equal to -4. So that was the mistake I made, which is now corrected. Next question, the last question for today's lecture is this. We continue with our discussion on set builder notation and inequations. This diagram has two inequations, A and B, on real number lines. So write A and B in set builder notation. So this one will be, A will be, remember x is belonging to the set of real numbers, such that we notice that there is a straight edge at -2 and this kind of a concave edge at 5. So what does that tell you? It tells you that x can be equal to -2 but less than 5. 5 is not included in the list of values, but -2 is. So this becomes the representation for set A. What is the notation for set B? Again, it is all values x such that x belongs to the set of real numbers where negative 4 is less than or equal to x is less than 3, because there is a concave edge at 3 and a straight edge at negative 4. So negative 4 is included, uh, 3 is not. So we have the two sets in set builder notation. What is the intersection? How do we represent A intersection B in set builder notation? So A intersection B would be everything in A and B. So intersection is A and B. So that would be all the numbers from negative 2, because I'm identifying, and I'll use a different color for this. I'm trying to identify the parts of the number line where it overlaps or it is common to both A and B. So it would be everything from negative 2 all the way up to 3, but not including 3. So A intersection B would be x. X belongs to the set of real numbers again, such that minus 2 is less than or equal to x is less than 3. So that's the part of the number line which is common to A and B. And why did we leave 3 out of it? Because 3 is part of set A, but it is not included in set B. So it is left out in the intersection. So now the important thing before we answer the last question, A intersection B naught, is to recognize what B naught is or B dash is. What is B dash? So let's write B dash here. What is B dash? If you look at B, you should be able to answer what B dash is. Everything that B is not. So it can be this part of the number line, which is less than negative 4, or this part of the number line, which is greater than or equal to 3. So let's first recognize what B naught is. So it consists of all the numbers which are real such that x is less than negative 4 and x is greater than or equal to 3. So the union of these two set of numbers gives us B naught, because those are the numbers that are not in B. So if you want to represent B naught, it is everything on this side. So this is B naught. So I'm representing, and so what I have drawn here is B naught. And what is A? Let me draw A as well. A is between negative 2 and 5. So A would be with a different color, that will help. Negative 2 is included, 5 is not. So this is A. The blue color is A. So this is blue color. So the red color on the number line matches A, and the blue color matches, uh, the red color matches B naught, and the blue color matches A. So it's possible to find the intersection of A intersection B and A intersection B naught. First, let's do A intersection B. So A intersection B will be between negative 2 and 3. So let me erase this and represent that. So A intersection B would be between negative 2. This is A intersection B. It is minus 2 to 3. Minus 2 is included and 3 is not, and this part is A intersection B. A intersection B naught, if you compare the two sets A and B naught, is 3 less than or equal to x less than 5. And that will give us the set like that. So we have represented A intersection B and A intersection B naught on the number line. So a quick summary: a linear inequation has linear expressions in the inequality. There is an example. Inequations can be represented on a number line, and we have seen several examples of that kind. For example, this number line representation indicates all real numbers which are less than or equal to negative 2. This inequation represents all real numbers between negative 2 and 2, but negative 2 is not included, 2 is included. And how do we write that? So this is the way you can represent a linear inequation on the number line. These are the rules that can be used to solve linear inequations algebraically. I have revised this a couple of times, so I will not go through them again. And being familiar with these rules is critical to being able to solve such questions. And that brings us to the end of the chapter on linear inequations. We have discussed uh, linear inequations with everyday examples, how we use it in conversations, inequations. They're quite common when you think of it. We have studied how algebraically we can solve them and how they can be represented graphically on a number line. With that, we wrap this chapter up. Next lecture will be on a new topic. Thank you for joining.